Hello everyone, welcome back. This is the fifth lecture of the series Electrical for GATE and IES. In this lecture, we will be discussing numericals based on Laplace transform. This is all about me. I have done BTech from BIT Misra and PhD and MTech from IIT Kharagpur. I have cleared GATE and Indian Engineering Services exams. So in this lecture, we will be dealing with transient analysis. We will be solving numericals through Laplace transform. So we will study about Laplace transform and then use it to solve numericals which involve transient analysis of the circuit. So first we will be discussing a little bit about Laplace transform. Laplace transform is basically a tool for solving differential equations. It converts a function of real variable to a function of complex variable. This transform is very useful as it converts differential equations into algebraic equations and convolution into multiplication, solving which is relatively easier. So how we do this transform? If we have any function f of t, small f of t, then its Laplace transform is given by capital F of s is equal to integral from 0 to infinity f of t e raised to power minus st dt for all t greater than or equal to 0, that is t is real number. Now this small s is a complex number and it is equal to sigma plus j omega. So we can solve this transform for many functions, like for unit step function ut, its Laplace transform is 1 by s. It is simply by putting ut in that function of the transform and then solving it. Similarly, we can solve this Laplace transform for various other functions, and it is shown in these slides. You can practice them, solve it yourself. If some problem comes, comment in the comment section. I will clear your doubt. And these Laplace transforms, they should be remembered, they should be committed to your memory so that you can use it directly in solving the numericals. In this slide, some more Laplace transforms of some more functions are there again. So now two theorems are also related to this: initial value theorem and final value theorem. The initial value theorem says that f of 0 plus, it means anything at any time which is just greater than 0, just after 0, it is equal to limit of s tending to infinity s f of s. And similarly, final value theorem is f of infinity is equal to limit of s tending to 0 s f of s. These functions, these theorems will be useful in solving some numericals. We will see them later. So this is the first numerical. In this circuit, both the switches are operated at t is equal to 0. It means one switch is closed at t is equal to 0 and other one is opened at t is equal to 0. We have to find the equation of voltage. Now once we operate the switches as shown, the equivalent circuit that will reduce to this one. One is short circuited, one branch is short circuited, other one is open circuited. So the equivalent circuit is like this. As the capacitor was initially charged to minus 2 volts, therefore at t is equal to 0, this voltage Vc G0 plus, that will be applicable in the circuit as shown. Now we simply write the circuit equations. Voltage Vst, that will be equal to voltage Vc plus 0 plus current I into the total impedance, that is R plus Xc. Now we transform it into Laplace transform. That will be equal to, as shown, Vs is equal to minus 2 by s plus I by s into bracket R plus 1 by Cs. And on solving this, we will get the voltage Vs is equal to 20 into 10 raised to power 3 divided by s square, and on inverse, taking inverse of the Laplace transform, we will get Vst is equal to 2 into 10 raised to power 3 t ut. So this is the equation of the voltage which was required. Now here I have shown one more methodology to solve the numerical. there is some flaw in it. You have to identify the flaw and tell in the comments. Now we move on to second numerical. In this circuit shown, the switch has been opened for a long time. It was closed for a long time and it is opened at t is equal to 0. Then we have to find the value of current through C. So we draw the circuit before t is equal to 0. The capacitor branch will be open circuited because charge has been accumulated on this and potential voltage is developed across it. So the equivalent circuit will be like this. Now we calculate the current through the circuit, that will be equal to 1 ampere. The voltage across the capacitor, that is equal to 4 volt. Now we draw the circuit after t is equal to 0. I mean t is greater than 0. That will be like this. Now we calculate the current IC, that will be equal to 4 by 4 equal to 1 ampere. Now we move on to the next numerical. In this numerical, C1 has been charged to 12 volts before switch is closed at t is equal to 0. We have to find the current IT for all t. So once the switch is closed, the equivalent circuit becomes like this. Now we write the circuit equation and solve for IS. We will get IS is equal to 12 C1 C2 divided by C1 plus C2. Now energy at t is equal to 0, that is equal to half of C1 V1 square. V1 is equal to 12 volt. Now let the capacitors get charged to Vc at t is equal to 0. Then the energy will be half of Vc square into C1 plus C2. Now equating both these energies, because energy will be the same. So equating both these and solving for Vc, we get Vc is equal to under root of C1 divided by under root of C1 plus C2 into V1. Now the current I is equal to C dV by dt. So C2 dV2 by dt, and V2 has changed from 0 to Vc at t is equal to 0. So IC will be equal to C2 into Vc delta t. Substituting for Vc, we will get IT is equal to C2 under root of C1 divided by C1 plus C2 into V1 delta t. Thus this current is an impulse function. Now we can see that there is some flaw in this approach which we used earlier. You have to find out the flaw and comment it. We move on to the next numerical. In this circuit, capacitor is initially charged to a 10 coulomb charge. We have to find the current 1 second after the switch is closed. We draw the circuit after the switch is closed. Then initial voltage across the capacitor, that is equal to Q by C equal to 20 volt. Now writing the network equation and taking Laplace transform and solving for IS will be equal to 80C divided by SRC plus 1. Taking inverse Laplace transform, IT will come out to be 80 by R into e raised to power minus t by RC. Substituting for t is equal to 1 seconds and R and C, we will get current IT equal to 14.7 ampere. We move on to the next numerical. In this switch S is closed at t is equal to 0. We have to find the voltage across inductance at t is equal to 0 plus. So we will use these concepts. Current across an inductor and voltage across a capacitor cannot change instantaneously. You should commit this rule to your memory. It will be used again and again. So therefore at t is equal to 0 plus, the circuit reduces to this one. Now the voltage across inductor at t is equal to 0 plus, VL0 plus, that is equal to 10 by 5 into 2 equal to 4 volt. So by using the concept, this numerical is solved very easily. That's all for today. Thanks for watching the video. If you like the video, please share it with the relevant audience so that more people can be benefited from it. If you have any suggestions, please write in the comments. If you have any doubts, please write in the comments. That will be taken care of. Thanks a lot.